All right, next up, Chapter 4, PowerPoint B. At the end of the last PowerPoint, 4A, we talked about low clouds, middle clouds, and high clouds. Now we're going to talk about clouds of vertical development, which actually can encompass all three of those height ranges, all three, low, middle, and high. And the most obvious one we'll talk about are cumulus clouds, which tend to look like a piece of floating cotton or pieces of floating cotton with a sharp outlines, a very flat base usually, and a very dome-shaped top. This indicates that there are bubbles of air that are rising and are becoming somewhat unstable as warm, moist parcels of air rise, expand, cool, and then condense, and then clouds form. The top of the cloud notes the vertical limit of rising air. Usually there's lots of blue sky between the cloud elements, and what this means is that between these clouds the air is actually sinking rather than rising. These are often referred to as fair weather cumulus or cumulus humulus in the Luke Howard classification dating back to 1803. If the edges of the clouds are ragged, then they're called cumulus fractus. Then we see towering cumulus in the top picture. Then the clouds start to resemble a head of cauliflower in the grocery store, if you know what I'm saying. These can be single clouds or they can form in lines. This is the same picture I used in a previous PowerPoint showing how warm, humid air rises into a cool, unstable environment. The air quickly cools, it expands, and then condensation occurs, and then you get these towering clouds that form. You can get showery precipitation from these clouds for brief periods of time. And then the bottom picture, the cumulonimbus. This is the thunderstorm cloud with strong updrafts and downdrafts. The bases of these clouds can be as low as 2,000 feet above ground level, but the tops and the strongest thunderstorms can exceed 39,000 feet above ground level. Especially in strong or severe thunderstorms, which we will discuss in a future chapter. They can produce violent weather, and they have that flat, classic anvil-shaped top. So towering cumulus and cumulonimbus. It's also important to talk about some unusual cloud formations. Lenticular clouds are caused as moist air crosses a mountain barrier. They can be layered kind of like pancakes on a plate. You know, you make a breakfast in the morning. Banner clouds are lenticular clouds that extend downwind from an isolated mountain peak for dozens of miles. Pileus clouds are clouds, not pictured here, but they're pictured in your book, that can form on top of a developing cumulus cloud, kind of like a lenticular cloud that forms on the top of a cumulus cloud. And most dramatically, mammatus clouds, which may often form on the underside of cumulonimbus or thunderclouds, especially when the thunderstorm is in the dissipating stage. This is a really dramatic example from your textbook of mammatus clouds and indicate a very unstable atmospheric condition. Now, let's go from the surface and talk about cloud observations from space. Now, of course, probably all of you are, well, you're young people, relatively speaking. I'm not afraid or ashamed to say that I'm 60 years old myself. But we have only had the capability of detecting clouds from space since April 1st, 1960. I was almost 8 years old then when the first weather satellite was launched, called TIROS-1. And it was a very crude satellite platform that orbited in a polar orbit at a low altitude, about 500 miles or so above the Earth's surface. And this satellite used a television camera to take pictures of clouds. So it was difficult, unless you were really, really trained, to be able to discern the difference between, say, cloud masses and snow that was on the ground. Today, we have much more sophisticated sensors aboard those satellite platforms that do much more than just take pretty pictures of clouds. There are two basic kinds of weather satellites. One is called a geostationary satellite. And these satellites orbit the equator at the same rate that the Earth spins on its axis, so that they take pictures from a fixed spot, allowing a continuous monitoring of a specific region of Earth's surface. They are positioned about 22,300 miles above the Earth's surface, which is the proper altitude for a geosynchronous orbit, meaning that they'll take a picture from the same place at the same time, usually in half-hour intervals, sometimes in 15-minute intervals. This is a real-time data system, as close as we can get to real-time anyway, and these images are transmitted immediately after they're captured to weather people for analysis of those features. And because it's taking a picture or pictures from the same place all the time, we can do time-lapse movies to show a moving sequence of clouds to aid forecasters. When you see the satellite pictures on the TV weather reports, you're seeing satellite images captured and looped from geostationary satellites. Then there are the polar orbiting satellites, which orbit closely parallel lines of longitude. In other words, the north-south lines that we put on maps, the lines of longitude, the polar satellites pretty much follow these lines of longitude. As the Earth spins eastward under the satellite, of course, is monitoring a new area west of the previous pass that it took on its next orbit. So it all has to sort of be stitched together. But the great advantage of polar orbiters is that because they don't orbit 22,000 miles above Earth's surface, they orbit only about 500 miles above Earth's surface. They give us much sharper images of polar regions because the closer you can get to Earth's surface, there's a lack of distortion. When you're 22,000 miles up, those images are somewhat distorted because you're so far away from the Earth and you have to take into account the curvature of the Earth. There are various sensors on board these satellites now. One is called a radiometer, which allows observation of clouds both daytime and nighttime by detecting radiation coming from the cloud tops. Bottom line is this. During the daytime, you take your camera outside, and if it's sunny or cloudy, at least you have daylight, you take a picture. At night, you have to use a flash. Well, this is kind of a crude analogy, but when you use a radiometer, this senses radiation being emitted from the cloud tops, so we can tell which clouds are high, which clouds are low, which clouds are warm, and which clouds are cold, even at night when the part of the Earth we're taking a picture of is in darkness. We can also detect with these radiometers radiation from atmospheric gases, which enables us to analyze temperature and moisture content of the atmosphere from space. The advanced radiometers are called imagers, and they provide better resolution images, sharper images than ever before. Sounders on the satellites give us accurate profiles of temperature and moisture at different levels of the atmosphere, which is kind of amazing that we can do this from space. Visible cloud images are only available when that particular part of the Earth is in daylight. That's radiation that is reflected from surfaces. So when a particular part of the Earth is in darkness, we rely on the infrared imagery, which analyzes radiated or emitted energy from cloud tops, not reflected energy. This, as I mentioned briefly before, enables us to differentiate between high clouds and low clouds and warm clouds and cold clouds. Now, some of these temperature differences between cloud masses are quite small, so science enables us to employ what we call computer enhancement, often with grayscale or color enhancement, in order to differentiate between the subtle features, temperature features in these cloud masses. There is also special infrared water vapor imagery that enables us to detect air motion in cloud-free areas. We can actually detect batches of water vapor this way in the upper atmosphere. This is a big help to forecasters. I'll show you some examples of these pictures in just a few minutes. So, how do these infrared sensors work that enable us to take cloud pictures when a particular part of the Earth is in darkness? Well, generally speaking, here's how they work. The lower the cloud, the warmer the temperature of the cloud is, of the top of the cloud is. Warm objects emit more infrared energy than do cold objects, and so the resulting images often use this grayscale gradation that I mentioned to distinguish between clouds of different temperatures. The darker cloud masses, the dark gray ones, are warm clouds or low clouds, and the bright white on the grayscale indicates a cold cloud top and a very high cloud in the atmosphere. We also color enhance these images, enable to more precisely separate cloud masses of particular temperatures, because sometimes the nuances can be quite small between different parts of the cloud structure with respect to temperature, depending on how high the cloud structure is above the surface of the Earth. All right, so what follows is a sequence of 3 satellite images taken at the same time of day, on the same day, and from the same place. This is from Wednesday, January 2nd, 2013, at 2030 Universal Time Coordinated. Remember, there's 8 hours difference between London and the Pacific part of the United States. We're in the Pacific time zone. So if you subtract 8 hours, that puts us 12:30 p.m. Pacific Standard Time. So this is right around lunchtime on Wednesday, January 2nd, 2013 in our time zone. I will show you first a 4-kilometer resolution visible image, the kind of picture we can only get when we're in daylight, a 4-kilometer infrared grayscale image, and then I'm going to show you an infrared water vapor image. Actually, I think now that I think of it, the infrared image is not a grayscale, but it's a combination of grayscale and color enhancement. So the coldest cloud tops are actually in a color scheme. So here we go. This is the first image, which is a 4-kilometer resolution visible image. Once again, this is taken at 12:30 p.m. on Wednesday, January 2nd. You can see that most of California is clear. You can see the snow-capped Sierra, and you can see a patch of fog in the San Joaquin Valley. And then you see that cinnamon roll-like swirl west of the Northern California coast. That's actually a storm system that's trying to come in. So here's the 4-kilometer resolution visible image. I'll now dissolve to the 4-kilometer color-enhanced infrared image. So the colder cloud tops are the ones that are seen in the darker red or magenta and in the green. The warmer cloud tops are the grayscale and lower clouds. So this gives you a different perspective. Now we'll go to a special image called a water vapor image. This is the same 4-kilometer resolution taken from the same place at the same time of day, 12:30 p.m. Pacific Standard Time on Wednesday, January 2nd. This enables meteorologists to determine areas where water vapor is concentrated in the upper atmosphere. The black or orange areas indicate very dry air, and the green to orange areas indicate very wet air in the atmosphere. So this is certainly a big aid to forecasters. One of the really interesting things that we can do now with these satellites is to get some idea of how much rain is falling out of a storm system. This is especially important in the tropics between 35 degrees north latitude and 35 degrees south latitude on either side of the equator, where we're dealing with tropical cyclones and hurricanes, which we'll cover in a future chapter. This is called the TRMM, or Tropical Rainfall Measuring Mission. This enables us to monitor clouds and precipitation between the latitudes I just mentioned, essentially the tropics, and we can actually get 3-dimensional images of infrared visible satellite imagery to see how much radiation is being reflected or emitted from the cloud surfaces, and we can also get a precipitation radar. This enables meteorologists to determine rates of rainfall per hour, which is essential in forecasting how a hurricane or a tropical storm will affect a coastline once it comes onshore. The Tropical Rainfall Measuring Mission, another one of the more sophisticated tools that meteorologists have in their toolkit. This ends Chapter 4 PowerPoint B, and in fact, our two PowerPoints for Chapter 4.